In this video, we're going to work a problem where we use a position vector to find a unit vector in the direction of a known force, and then use that unit vector to get the force vector. Okay, so it says if FB is equal to 700 newtons, this is FB, and FC is equal to 560 newtons, that's FC, determine the magnitude and coordinate direction angles of the resultant force acting on the flagpole. So you can imagine that these cables, you know that the force, the direction of the force has to be along the line of action of these cables. And maybe you know the magnitude, maybe there's a load cell here or here. You know the magnitude of the force in those cables, but how do you find these forces as vectors? Because you want to get the vector sum, right? To get the net resultant sum on the flagpole. So how do you find these forces as vectors? Well, okay, let's start with FB. What we want to do is find a unit vector in this direction, in the direction along this cable. We can do that by finding the position vector from A to B, and then dividing by the magnitude of that vector, and we'll get the unit vector in the direction of FB. Then just multiply FB times that unit vector, multiply the magnitude of FB times that unit vector, and we've got the vector FB. So let's do that. RAB is what? Okay, so a position vector, it's X, what we do, XB minus XA. For the I hat component of RAB, what's XB minus XA? Okay, so XB is 2, okay, minus, what is XA? This is A is at the origin, well, at least in the XY plane origin, so 0. That's I hat. Okay, what is YB? YB is minus 3. Okay, so YB minus YA, YA is 0. Okay, now ZB minus ZA, what is ZB? ZB is 0. ZA is what? Positive 6. Okay, so we've got 2I hat minus 3J hat minus 6K hat, right? Going from A to B, we go minus 6. You see, we're going from A to B. Okay, so that's RAB. Now, what is the magnitude of RAB? Well, 2 squared is 4, 3 squared is 9, 6 squared is 36. 9 plus 4 is 13, 36 plus 4 is 49, so 7. Okay, so the unit vector in the AB direction is what? Divide RAB by 7. 2/7 I hat plus or minus 3/7 J hat minus. Okay, so now we can get FB. Just multiply this unit vector, this UAB, times the magnitude of force B. So 700 times 2/7 I hat minus 700 times 3/7 J hat minus 700 times 6/7 K hat. So in each of these, this simplifies to 100. So FB is 200 I hat minus 300 J hat minus 600 K hat. All right. Now let's just do the exact same thing to get FC. So what is RAC? Okay. So xc minus xa is what? So xc is 3, and then xa is 0. Okay. yc is 2. ya is 0. Okay. zc is 0, and then za is 6. Okay, so we've got 3 I hat plus 2 j hat minus 6 k hat. All right. Now, the magnitude of RAC is equal to, so 9 plus 4 plus 36. So this is 7 again. All right. So the unit vector in the AC direction is 3/7 I hat plus 2/7 j hat minus 6/7 k hat. All right. So FC is equal to, and so we multiply 560 times this. Okay, plus minus okay, so FC is equal to 560 divided by 7 is 80. So we've got 240 I hat plus 160 j hat minus 480 k hat. Okay, so we've got FB and FC as vectors. So now we can just, to answer the problem, they want the resultant force, so we just add those two vectors. Okay, so what is FB plus FC? All right, 200 plus 240 is 440. Okay, we're going to have a minus here because minus 300 plus 160 is minus 140. Okay, and then minus 600 minus 480 is minus 1080. Okay, so now one of the things that this question wants is the magnitude of this FB plus FC. So we'll call this F resultant. So the magnitude of F resultant is what? Okay. Square root of 440 squared plus all right. So we've got plus, oh, no, wait. This is 140. Okay. plus 117.46. Let's call it 1175. Okay. Now we need to get the coordinate direction angles of this resultant force. So the alpha, beta, and gamma. And we've done this a bunch of times in previous problems. Any force vector in 3D or 2D, but when we think about coordinate direction angles, we're usually talking about in 3D, but you can apply this in 2D. It's cosine of the magnitude of the vector times cosine of alpha I hat, plus the magnitude of the vector times cosine of beta j hat, plus the magnitude of the vector times cosine of gamma k hat. So we know the magnitudes and we know these components. So we can say we will say 440, 440 cosine of alpha is equal to the magnitude, or no, wait, no, sorry. The magnitude, so 1175 cosine of alpha is equal to 440. Right? So alpha, we say 440 divided by 1175. Okay, now that's cosine of alpha, not just arc cosine of this. 68 degrees. See? So now 1175 cosine of beta is equal to minus 140. So beta is equal to, you want to make sure you use the minus. 140 divided by 1175. Okay. Arc cosine 96.8 degrees. All right. Now 1175 cosine gamma is equal to what? Minus 1080. So gamma, we've got minus 1080 divided by 1175. Okay, and arc cosine, inverse cosine, 156.8. And there you go. We've got, this is magnitude of the resultant. And this is the direction of the resultant. In 3D, we use these coordinate direction angles. But again, you can absolutely apply this in 2D, these coordinate direction angles, but like gamma, like assuming you're in the XY plane, but you could do it in any plane, but let's just say the XY plane, well, then this gamma is going to be 90 degrees. That means you're in the XY plane because the angle between the vector and the z-axis, the positive z-axis, is 90 degrees. And that's why when you look at the components of the vector, you'll have magnitude of the vector times cosine of 90, which is 0. So there is no component in the z. It's really important that these coordinate direction angles, it's not like you go into a different world when you go into 2D, not at all. These coordinate direction angles completely describe vectors in 2D or 3D space.